Now we move on to the surface roughness measurement. Normally the surface roughness measurement methods used into the normally the finishing processes or the machining processes. One is by inspection and comparison, or inspection by comparison. Another one is direct instrument method. The inspection by comparison method, if you see here, what is normally will be done, these methods are assessed by the observation. Basically just you see that product and you just tell whether it is finished or not finished. It is a exclusively a comparison method, qualitatively comparison, whether this is good or the another object is good, like that. Okay, these are the methods of qualitative analysis. I said no, these are the qualitative analysis. That means that only you can say that Ram is a good boy. You cannot say Ram is a 90% good or 80% good or 40% good. Okay, so for that purpose what I mean to say is that you can say whether the product is good or not good. You cannot say this is 80% good or 70% good or 50% good or something. Okay, that means that you can say that this is a qualitative. Hope the undergraduate students might have understood that the difference between qualitative and quantitative is, if you want to say this is 50% or 40%, that is called quantitative. You are specifying the quantity. Okay, if you are saying whether good or bad or quality is good, quality is not good, that is called qualitative. Okay, for now this inspection by comparison method is goes by qualitative method. The surface texture or the surface is treated by comparing with that of the specimen of the known roughness value and finished by the similar machining method. Actually, if at all I want to check particular component, assume that I want to check a particular component by abrasive flow finishing process or any other polymer assisted abrasive finishing process. I will have a master sample by known input conditions and other things. I have finished one. Let me explain you in this way. So I have a grinded sample or the ground sample which is done by the grinding operation. Master sample is there and the customer gave me this sample is you have to achieve approximately this. Now I have a master sample and the company has produced some 1000 samples. So I just compare. I will take both into the hands and I will see, okay, this is master and this is what we have done. Okay, if it is okay, then I am selecting. If it is not okay, I am not selecting, like that. Okay, that is what is finished by the similar machining operation or a finishing operation. Then you just say whether it is okay or not okay. Though these methods are rapid and results are not reliable, because you may get sometimes biased or you may get okay, this is okay, okay, like that also you can just keep it. So that's why this is not reliable, because they are misleading if the comparison is not made with the surface produced by similar techniques. Why I am saying is that assume that my master sample is procured from some agencies and you are having a sample that is produced by grinding. If you do not know what is this master sample has prepared from which process, assume that this is prepared from a lapping process and whatever you got, the lot of the samples that is produced by the company is a grinding process. If surface finish is not matching or if it is matching, it is okay. If it is not matching, then see the surface lay directions will be different. Your application may be somewhat lapping oriented applications, but the surface roughness that you are going to get or the predominant surface roughness directions on the grinding sample will be a straight line type of, but in lapping it is not, it will be random and mostly it is circular or something. So sometimes these small errors may mislead. So inspection by comparison, these various methods are available. One is visual inspection method, then touch inspection method and the scratch inspection method and microscopic inspection method, surface photographs and micro interferometer and other thing, Wallace surface dynamometer and other things. Okay, reflected light intensity, these are the some of the methods. Okay, one you can see here how you can see using the line scan camera and other things. What people can do is the parts are moving on this belt and whenever the part will come into the picture, it will happen, it will take the image and it will give the inspection. and it will inspect the surface whether the surface is okay or not okay and other things, and it will be decided. And the same thing, camera output will be there, and you can see here what will be the image of that. Based on this, the person who is sitting in the computer or automatically robot system or something, they will select whether the part is acceptable or not acceptable. And another methods also are there. So these are the so many methods which one can follow, and another one is direct instrument method. Direct instrument method follows quantitative analysis. You have an instrument and it will give you a definite value, whether the roughness is 1 micron, whether the roughness is 0.5 micron or something. That is qualitatively it will convey. These methods enable to determine the numerical value of the surface finish or the surface roughness of any surface by using instrument of stylus probe type of operating based on the electrical principles. So, there is a contact method where you will have a probe. Assume that this is my surface. I will have a probe. This probe is connected to some electrical sources. So, lot of things are there which is less importance for the mechanical engineer. Just a stylus will be there, it will be moving on the surface and you will get the value. Similar things you have also understood in the previous slides also. Few instruments, one is profilometer, profilograph and Taylor-Hobson Teleri-Surf and surface meter and other things are the common methods. The pocket surf is there, one method, and another is surface analyzer. These are the two common methods which normally we do at our laboratory. One is the pocket surf. The pocket surf normally what you can do is, this is the probe which you can see here, and beneath that one what you have to do is you have to put your sample. Just you put your sample and you just press a knob. Knob will be there on this side. You just press a knob, automatically what it will do, the probe will reciprocate like this and will give you a digital display, okay, so that you will get the value. Normally this pocket surf is a rough method of estimating. Okay. To suppose I want to know what is the approximate value and other things, then you can go for it one. Or if at all I want to measure the surface roughness value of a cylindrical rod which is mounted on the headstock of a lathe machine, you can go for pocket surf, and this will give you a rough idea about what will be the approximate surface roughness. If at all I want to know more, then I will go for slightly upper side, that is Surface Analyzer 5000, where I will keep my sample here. This is my probe. I will keep my sample here, and similarly I will operate. So the probe will reciprocate and will give you a roughness value. In this Surface Analyzer 5000, it will give normally this type of profile, and this from the profile you can give the value also, and you can get the profile also. That means that it is a 2D profile, 2D surface profile you will get. Okay. So now from this one, how you are not only getting the value, but also you are getting what is the surface roughness along that particular line. Okay, that is called 2D surface profile. Now what is the other way or more advanced way is non-contact interferometer, okay, surface interferometer and other things. This will give you a complete area wherever it can focus. Okay. From this you will get a 3D surface view. What you have seen in the previous one, pocket surf is going to give you only the digital value, and the second one, the surface profilometer, Federal Surface Profilometer will give you a line scan. Now you have a Taylor-Hobson 3D surface profilometer which works on interferometry and other things, which will give you a 3D profile. So this is the advancement that is going from a digital value to a line, from a line to a plane. So if at all I want the line, here I can get. If at all I want a digital value, if at all I want to measure a line, surface roughness, just I plot a line here, and this line will give me a surface profile like this. Okay. At the same time, assume that this is 2 microns. It will also give you a digital value of 2 micrometers. Both it will give. So, this is slightly advanced compared to those two techniques. And now you can measure various things also. So, once you got a 3D surface profilometer, you can also get the average surface roughness value of that particular area also. In a 2D surface profile, you can get only about that particular line. Okay. In the 3D profilometer, you can get also the area surface roughness value. That will be much more accurate. Whenever you are going to showcase or whenever you want to sell your product, normally people may ask you overall area surface roughness. So, for that you have a sample, then you have to do at minimum at 5 to 10 places, and you have to give the area surface profile, like the 3D profile. This is average surface roughness of a surface that is scanned, and you can also give the surface roughness value along the line, particular line, so that you can understand which area the surface roughness is more, which area surface roughness is less, but on an average what is the average surface roughness of that particular surface. Okay. This is about the digital value. It is a single value where you do not know the surface roughness profile. Next you will have a surface profile of 2 dimension like this, and the furthermore you will get a 3D surface profilometer, and this is what the surface roughness. Now we will see what is the importance of taking a surface profile in a 3D spectrum. That means that 3D profile is required to for us. That is what we will see here. Assume that I have two surfaces of surface roughness x, then can you use both the surfaces into the practical application? Maybe, may not be. For that purpose, I will show you one example which is finished by MRAFF process. That process you will get in the upcoming classes, where magnetorheological finishing and abrasive flow finishing principles are clubbed. Okay. So, whenever you are going to study about magneto-abrasive flow finishing process, you will get about magnetorheological abrasive flow finishing techniques. These are the two surfaces finished by magnetorheological abrasive flow finishing. That means MRAFF. Okay. These are the finished by two techniques, magnetorheological abrasive flow finishing process. Now we will see two surfaces. What is the difference? Here you see this is finished. We do not bother about how it is finished and other thing, that we will see in the when the process is there. We bother about the surface. Normally we bother about average surface roughness value of this particular surface. This is the atomic force microscopy image, where MRAFF process has done for 2000 cycle with silicon carbide as its abrasive particle, and you are going to get a surface. But what you have to note here is the surface roughness value is 0.1 micron. If you see same MRAFF process, here also you are going to get approximately same value of 0.1 micrometer. Here it is finished with diamond particles. Okay. You do not bother about the process and whether diamond or whether silicon carbide. What you have to bother is you can see the same value of surface roughness, but two surface morphologies or two surface profiles or two surface topographies. This topography is slightly rough surface compared to this one, but the value of both the surfaces is same. Now you can understand, if you are not going to get the 3D profiles or 3D surfaces, then you would have thought, assume that you would have taken only digital value. If you would have taken only a 2-dimensional value, like a 2-dimension, this is 2D profile, 2D profile, you may mislead. If you take a 2D profile, this profile is bit rough compared to this profile, these 2D profiles, you may mislead and assume that you are going to choose the rougher one. Life of this component will be much less or slightly less compared to other component which is smooth compared to the surface. Okay, that's why the people who are doing the research and other things, they should go for 3D surface profiles if you have the facilities available at your institute. Okay, so that you will get a good knowledge about the complete overview of the surface. This is the beauty about taking a 3D surface profile and analyzing its 2D surface and getting the digital value also. Okay. So, 3D profile will give you 3D image, it will give you 2D image, and it also give a digital value. That is why if you have a 3D surface profilometer or atomic force microscopy, then you can get all other things also. Now, we will see about surface roughness representation, how the surface roughness is represented. As I said, lay is nothing but predominant direction of the surface roughness. First is parallel to the plane projection. Normally, if you are getting the surface like this, it will be represented by like this. If it is perpendicular, it will be represented like this. If you are measuring a particular surface, and its representation you can see here. Crossed one you can see like a knurling operation and other processes, normally represented by X, and multi-directional. If it is multi-directional by any other advanced finishing processes where the abrasives have free to move in that direction, you will get this type of thing. And the circular related to the center of the surface, these surfaces you can get like this. Normally you will do on facing operation and other operations, you will get this type of circular pattern or circular lay, and R represents the radial relative to the center of the surface. These are the surface representations and the basic symbols. Now, how to represent? We know what are the lay patterns, whether it is parallel, perpendicular, circular, crosshatch pattern or multi-directional or radial directional. These are the surface patterns. Now, how I have to represent in the form of symbols. So, the basic symbol consists of two legs or unequal length, which is at 60 degrees, and the symbol must be represented by a thin line. If the material removal is by machining, then is required bar is added on a symbol. That means that this is the basic symbol. If at all I want to go for machining, then you have to add a line. If the material removal is not permitted, then you have to represent by a circle here. And if the special surface characteristics has to be indicated, the line is longer arm any above symbol. That means that if the any surface characteristics, special surface characteristics has to be mentioned, then you will get a additional one. Okay. Hope you got it. If this is a basic one, if it is machining, if it is no machining or any special characteristics, if you want, then you should have this type. Okay, the values how you are going to represent. A is representing the surface roughness value. Basic symbol with A, that means that this is the surface roughness that I want. You use whatever the process that you want. Okay, this is one. In the second one, I want the surface roughness where you have to achieve the surface roughness by machining operation. In the third one, you have to get the surface roughness not by machining process. You use any other process. Okay. If necessary to impose maximum and minimum values of the surface roughness, both values also can be expressed like this. One can be maximum, one can be minimum. That means that A1 is maximum limit and A2 is a minimum limit. For example, if I want to get 1 micron, so A1 will be maximum 1.0 micrometers and A2 is 0.9 micrometer. Okay. Like that I can represent in the surface profile, and I can say that within this limit you can get. Indication of surface roughness, if you see that it is surface texture can be produced by any one particular production method, this method shall be indicated also. That means that if at all by this line, assume that I am talking about figure 1, this line represents machining process. It is, if this portion is not mentioned, that means that you can use any method. If the special requirement is given by the customer, then you have to do the machining, and it is done by the milling process only, or you have to perform the surface roughness. A is a surface roughness have to be achieved by machining, and that too milling. That is what the meaning of this. Then if you see the machining allowances where necessary to specify value of machining allowance, this shall be indicated at the left of the symbol. This is called machining allowance. Okay. What are the allowances that you have to give? That can be represented at the left side of the symbol. And overall what we can see here is complete representation. You can see here A1, A2 you already know, that is the maximum value of the roughness, minimum value of the roughness value, and the lay pattern. What type of lay I want, whether in this case I want a parallel surface, that you can achieve by any process, because there is no line here. So, if it would have been there, then you have to do by only machining. If it is not there, you can do any, whether you can do the machining process, whether you can do another process also. So, but the pattern they have mentioned is parallel. That means that you have to, mostly you have to do like grinding process, and the maximum roughness spacing also they have mentioned. Okay, this is roughness is there, and the spacing between 1 and 2 also mentioned. At the same time, waviness height you can give here, maximum waviness width also you can mention, special requirements, and you can also mention the cutoff length. That means that you have seen the cutoff length. Cutoff length normally have to be less than your waviness. Okay. If it is normally less than, then what will happen? The waviness cannot be into the roughness. If it is embedded, then what you are going to get is a profile roughness. As you already know, this is my surface roughness and this is my waviness. If you club both, what you are going to get is the profile roughness. This is RA, this is WA, and this is profile average roughness, PRA. Okay. This is how you can represent the complete things basically. If at all you want still more complex, you can go ahead, and you can see here what is the flat lapping and reaming surfaces. Normally you can see the lay pattern like this, cross hatch patterns also will be there, and the grinding surfaces also will be there. You can get many types of surfaces, and these are nothing but the lay. You know the value that is called only roughness value. If you measure in this surface like a line, you will get a digital value, but sometimes people will specify the lay like cross hatch pattern. This is cross hatch pattern. Normally this is required for your automobile engine cylinders. Okay. Why you require it? Because your lubrication and other things will be taken care, and this lubricant will stay in these cross hatch patterns and will have the smooth piston movement, and for that purpose normally people do the honing process. Okay. The surface morphology and metallurgy in polymer assisted abrasive finishing processes, if you see here, we have to understand why we go for polymer assisted abrasive finishing processes. For example, if you are going for grinding process, whenever you do the grinding process, what will happen? Your forces, normally your radial force and other forces will be approximately 50 Newton to 150 Newtons normally. Because of this high amount of forces, the surface roughness you are going to get is rough, At the same time, what you are going to experience is the damage of the workpiece by burning and other things. You can see here the burning, or there will be a pit formation is there, and these are all observed whenever there is a forces. That is why in polymer assisted abrasive finishing processes, you are going to experience the finishing with respect to a liquid type of tools. Polymers will be there, rheological additives will be there, some liquids, then some solids will be there, and abrasive particles will be there. Okay. A grinding wheel is a solid body. Polymer, rheological abrasive fluids, these are all a liquid or a semi-solid. Obviously, whenever you hit with the semi-solid and wherever you hit with the solid, the forces will be much higher than the experience that you will do with respect to liquid or semi-solid. Because of which you can also observe there is a change in the metallurgical properties also. The surface roughness and elemental analysis, if you can see here, lot of damages will be there for the grinding surfaces, and you can also see the elemental mapping also. You can see there will be a change in the surface morphology. The parental material, whenever you see the parental material, then this is called elemental mapping. Okay. You can map the elements. For the same pictures, you can see how the elements can be mapped, and you can check. And you can see the grinding surfaces. The grinding surfaces, as I said, the forces are very high. Forces in grinding are very high, because of which what will happen, the surfaces damage will be very high, and you can see the surface damages, ploughing. Okay. The mechanism of grinding, material removal, this abrasion is there, ploughing and rubbing, three mechanisms are there. If there is abrasion or shearing, there won't be much problem. If there is a ploughing, normally the material that removed from one place will just smear into the other place. Okay, that is called the ploughing. And rubbing, anyhow, if you give insufficient depth of cut, what will happen? The grinding will rub against and it will burn. All these things are because the interaction forces of grinding process or solid based tool like lathe, the turning process also, the forces are very high. Whenever you talk about the finishing process, your forces should be as minimum as possible, so that the depth of indentation will be very less, so that you can get the microchips or nanochips and you get a good surface finish. What is I want to convey from these slides is that why we are going towards polymer rheological fluids or polymer assisted abrasive finishing processes, that these finishing processes are confined to finishing processes, and the force experiences during this processes is normally 5 newtons to 10 newtons. So, that means that the finishing is very smooth. Whenever your requirement is finishing, then you have to go mostly for either polymer rheological abrasive finishing processes or magnetorheological finishing processes and so on. Wherever there is a liquid type or semi-solid type is there, you can choose rather than the solid based tools. As you can see here, how the grinding surfaces also can be polished. This is some of the example of abrasive flow finishing, where you can see these are the grinding marks. These grinding marks also can be polished by this polymer rheological abrasive medium. You can see small scratches that are there on this, which is moving perpendicular to the grinding lay pattern. This is the grinding lay pattern, this is the AFF lay. Okay. This is grinding lay. Smooth surface gradually increasing, and the final AFF lay you can clearly see here, that is predominant surface roughness directions, and it is polished. And you can see the surface roughness improvement from 0.7 micrometers to 0.3 micrometers, where the dominating surface roughness characteristics of grinding process is finished using abrasive flow finishing process. This is the beauty about polymer assisted abrasive finishing process. Okay. That is why you are going to study about these processes. Some of the processes also you will study about drill bit guided abrasive finishing process. This is the grinding surface, and this is deep drill bit guided abrasive flow finishing process. Okay, you can see the transformation, how the surface is transforming. This transforming is required whenever you want mirror like surface roughness and other things. Grinding process as per current scenario is considered to be one of the machining processes only, because we are moving towards advanced finishing processes and other so on. And you can also see the surface morphology, lot of debris are there, these debris, and you can also see the burrs which are unremoved. Okay, these burrs are there and some of the debris are there, some ploughing is there, because whenever the abrasive particle is moving here, there is a smearing of the material or deforming the material towards the next one or the previous one. Okay, from this slide what I mean to say is that the importance of polymer assisted abrasive finishing processes, which is this particular course. Okay, those people who want to do the research in this area is enormous. Many people have already done, and still there is a scope for developing the abrasive flow finishing process and various advancements in abrasive flow finishing process, hybrid abrasive flow finishing process and other things. These are all I will cover in upcoming classes also. Okay, so the grinding process is not the final finishing process, that is what I want to convey as per the nano surface is concerned. If at all you are happy with the micro surfaces, 2 microns, 1 micron, or you are happy with 1.5 micron, then grinding is a very good process. If at all you want like 50 nanometers, 100 nanometers, 75 nanometers, then you have to obviously go to the advanced finishing processes, and one of them is polymer assisted abrasive finishing process, which is the course that I am dealing with. The spiral polishing method also, some of the methods will use EDM process, electric discharge machining. As I said, that recast layer will have a resolidified layer. This resolidified layer, whenever it is solidifying, there will be a cracks, and if at all you want to put this into practical application, then what will happen? It will fail. For that purpose, you have to go for finishing of this one, and you can finish using spiral polishing method, and you can get the good pattern of the surface, and moreover you can remove the recast layer entirely and you can expose to the parent material. Now if you put this into the practical condition, then what you are going to get is the good life of that particular component compared to the previous one. That's why you have to understand the applications and some of the applications of the surfaces. These are all you may get again also whenever you see abrasive flow finishing process, the fuel injector nozzles that you have to finish. In these are the extrude hone company, they have specified. If you don't finish, it will be like this, and the fuel has to be ejected for the combustion and other things. If at all I want to eject X amount, if the surface is like this, very rough surface, what I cannot eject perfectly. In that circumstances, what will happen? That improper combustion will be there. For that purpose, you have to finish this, and better combustion can be taken place, and carbon monoxide and other dangerous gases won't evolve. So this may refer to this one. I am not saying the same, just refer, and this will refer to this one. So that if at all I have this smooth, the fuel flow very smoothly. Here if fuel has to flow, there will be obstruction. That's why you have to polish the surfaces, and one of the techniques people use is abrasive flow finishing. Abrasive flow finishing uses polymer rheological abrasive medium, and exclusively about abrasive flow finishing processes and advancements and other things we will see upcoming classes. And you can also see the polishing of some of the dyes, and these are all can be achieved by this polymer rheological abrasive medium. Okay. So Why we need the polymer assisted abrasive finishing process? Problem due to high forces involved in conventional machining and finishing processes, and less contact forces during advanced finishing processes, and better surface integrity. As I said, surface integrity means surface roughness or surface morphology plus surface metallurgy. Okay, M stands for metallurgy, here also morphology. To achieve nano surfaces or the surface roughness in the nanoscale, that means that 1 nanometer to 100 nanometers, like that, and deburring is required after grinding. You have already seen the surfaces are very rough and deburring is required, as well as some of the materials that are deposited on the neighboring valleys has to be removed. The material that is loaded in the valleys has to be removed. The finishing of advanced materials have to be done because the world is growing. As the world grows, what is thing? New materials are coming, ceramics are coming, glass ceramics are coming, biomaterials are coming. You have to polish or you have to finish. Whenever a component is there, like a Hastabular socket in a hip joint or a knee joint or any other application like cardiovascular stents, these are all to be polished up to a nano surfaces, because these are all directly going into a human, and if there is a high roughness is there, body fluids flow will be obstructed and this body fluids will stagnate in the valleys. Assume that my surface is like this, these body fluids will stagnate here, and nothing in this world is uncorrodable, and it will damage the material in these regions, and this will cause lot of other problems whenever you have a knee implant or a hip implant or any other biomedical implant. That is why you need to polish into a near nano surfaces, so that body fluids can easily flow on this one and there will not be much obstruction, and if there is stagnation of some fluid, it will be much less compared to the high rough surfaces. Okay. Summary of this one. So, introduction to surface integrity, we have seen why surface integrity is required, why not only surface morphology. Then we have understood what is surface morphology and we have gone to the first one, that is called, among the surface integrity, the first one which we have seen is surface metallurgy. Since we are mechanical engineers, we have just saw some of the glimpse and importance of the surface metallurgy, and if at all the people who are watching this may not be a good at metallurgy, many of you may be convenient with metallurgy, but some people who, if you are not comfortable, then you have to collaborate with the material science and metallurgy guys and you can get the collaborative work. Then we have seen to the importance of surface integrity in abrasive processes, and we have gone to surface roughness and surface roughness specifications and how to represent the surface roughness. Then at last we have seen the surface integrity in polymer assisted abrasive finishing processes such as abrasive flow finishing process, drill bit guided abrasive flow finishing process, spiral process and so on. Okay. Why I am telling the importance of this particular class of surface integrity is the surface integrity you will get in polymer assisted abrasive finishing processes is much better compared to your grinding process or any other conventional finishing processes. That is why you are going to study a good course where you learn about the fluids that are going to polish or that are going to finish the components. At the same time, there are some plastics, there are some polymers that are directly going to finish the workpieces instead of ceramics directly. If the ceramic is indented to a metal, assume that I have a knee implant that has to be polished or finished. In that circumstances, if you are putting a ceramic abrasive particles, then the interaction forces is very high, because one side it is a metal, on another side it is ceramic. So, interaction forces are very high. If I put the plastic abrasive particles which are embedded with the abrasives, small abrasives, then interaction forces will be much less. So, you will go through some of the mass finishing processes where polymers are also have role. You will also go through some of the advanced finishing processes where polymers play a major role. Thank you for your kind attention for this particular class.